All right, so today we're going to be talking about computing performance. So last class we briefly touched on this concept of execution time, throughput, and performance. We talked about these concepts of seconds per instructions in units, execution time. So you have instructions per second is throughput, and then execution time is just 1 over that. And when we go through these examples, you're going to see that proper use of units will always help you out in situations where you start getting confused. So in this case, I want to talk about the relationship between clock cycle time, clock rate, and what's known as CPI. CPI is clock cycles per instruction. So the clock time is the time for one clock cycle generated by the processor. So what does this mean? You got a 2 gigahertz processor, right? So what does giga mean? Billion, right? So you have 2 billion cycles per second, right? So if I'm setting this up, what we got here is just 2 times 10 to the 9 cycles per second. So that's what we mean by one clock cycle generated by the processor. So now in order to find that, we just take this and go 1 over 2 times 10 to the 9 because it's going to be one cycle. So how many seconds per cycle? So now we have 1 over 2 times 10 to the 9. That becomes 1 times 1/2 times 10 to the negative 9 seconds per cycle. So therefore we have met our definition, right? So clock rate is this number, which is the number of clock cycles per unit time, cycles per second, which is what we calculated here. And then, so you see here, clock cycle time equals 1 over clock rate. And then the CPI is clock cycles per instruction. So this becomes more complicated when we want to calculate this out. Now you can see a number of different ways to calculate the CPU execution time. Now what the CPU execution time means is I have a number of instructions, and each instruction takes a certain amount of time. And based on that, you have to be able to, all right, one thing, I videotape, so please do not take video or camera pictures of my lectures, thank you. Since I'm posting them online anyway, it's redundant. So CPU execution time. So you're going to have a number of different instructions that have a number of different clock cycles per instruction. And based on the clock cycles per instruction, and based on your clock rate and cycle time, you can actually calculate how fast the program is supposed to perform. So here we have CPU clock cycles times clock cycle time. So you have cycles over cycle time, which equals seconds per cycle. And like last lecture, I told you that we're going to have stoichiometry is going to cancel out, right? So therefore, execution time comes out to seconds. Same thing, now we have, instead of times, you have divided by clock rate. So if you're doing the units again, we have cycles. That's going to be divided by cycles per second. So therefore, that just becomes seconds again. Now, CPI means cycles per instruction. So you have cycles per instruction. So in order to get cycle time, so let's say you have an instance where you have the CPI. I've given you a problem as a CPI, and I'm telling you to find the time. And it's a quiz or an exam, and you cannot remember this equation. Here's the trick. I got cycles. I have a CPI, that's cycles per instruction. If I multiply that by the number of instructions, we get rid of instructions. And I multiply that by seconds per cycle. Gets rid of that. Now I have my CPU execution time. And by doing that, I've derived both of those equations. Because this is the same thing as divided by cycles per second. So just by using those units and keeping track of them, so that's why I think it's important to have those as topical guide objectives, because you forget the equation, you're on the exam, you know the units, you'll be able to derive the equation off the top of your head. So scroll past 130. So now, here's the thing. What we're going to learn is different site instructions have different clock cycle times. Now, this is intuitive. You think about it. If you're doing mathematics, let's say one cycle is required for addition. So if you're doing a multiplication, or let's say the same thing, addition or subtraction each take one cycle time. If you're trying to do multiplication and division, they're each going to require many more cycles because each one is going to be doing a addition or subtraction and then some sort of carry operation, right? So sometimes you'll see a problem where you'll have some sort of addition takes 1 clock cycle and then multiplication takes 10 and then division takes 20. So then what happens is in a given program over a course of millions and millions of instructions, you're going to have an average of 100 additions, 20 multiplications, 10 divisions, things like that. And you know for each instruction count how that's going to work. So we can actually derive a problem here. Let's just use that one here. So we have addition is 1, subtraction is 1 cycle, and then we have multiplication is 10, and division is 20. And we know that we have 20 addition, 20 subtraction, and let's say 10 multiplication and 5 division. So now we're going to use that and then use this equation here, which is average cycles per instruction. Given a benchmark, we actually can calculate what we expect the program to run in per given time. So this would just be number of instructions times average CPI. So this would be 20 times 1 plus, because it's a sum, 20 times 1 plus 10 times 10 plus 5 times 20. And then here we have just the sum of the instruction counts, which is this. So this just becomes 20 plus 20 plus 10 plus 5. Now on a quiz or an exam, that is a sufficient answer. I'm testing to see your knowledge of advanced digital systems. I'm not testing your ability to put numbers into a calculator. You struggle with that, you need to go back to 7th grade. I'm not testing you on that. It's not required. So as you'll see on these examples, I will actually leave them at what I consider to be an acceptable answer. Show me the equation, lay it out, plug the numbers in, move on. Does that make sense? So I'm going to go past 131 here and start talking about this example 1.5. So a program runs in 10 seconds on computer A, which has a 2 gigahertz clock. So what is 2 gigahertz here? Oh, and what I should have asked the question better. What term did we use to describe 2 gigahertz? Clock rate. Very good. And what's 10 seconds? What term? Execution time, right? So we have our execution time, which is seconds, and clock rate is what? 2 bit. And the units is cycles per second, right? So we have seconds and cycles per second. So we can already see where we're starting to go here. So this runs on computer A. Computer B runs the same program. That's an important term. In 6 seconds. But requires 1.2 times as many clock cycles as computer A. So what is the clock rate for computer B? Now, the reason why this is important, if you're looking at phrasing, if it's the same program, what does it mean? Bingo, very good. It's the same number of instructions, right? So if you're taking these equations, anything that involves instruction just cancels out automatically because it's the same number. So you don't even need to know. All you know is that it is a program. So what we're doing here is we're going to try to find the CPU time for computer A and then try to reduce it down. So step 1, we have our 10 seconds. We're trying to find the time. Like we noticed earlier, we have seconds equals time 10.
Are we actually going to?
Oh yeah, no, actually we're solving. Oh no, we're okay. Yeah, well that's what I did. See, it's exactly what we're doing. Okay. So we are solving for this equation and then solving for cycles, right? So getting back to what I was saying before, what we're having here is we start with seconds times cycles per second, right? So we know we have 2 gigahertz, so we're trying to find the exact number of cycles, right? So we know that we have 10 seconds, and we know that we have 2 gigahertz, so that comes out to 20 times 10 to the 9 cycles. So how does this, without looking at the next value here, why is that important? Go back to this equation and look how I'm phrasing it. What's the important part about computer B? 1 point, yeah, exactly. So that's what we're trying to find, but everybody else pointed out the 1.2 times, right? So what do you think we should do next? If I have the number of clock cycles that it takes to execute computer A, and I have, just multiply by 1.2, right? So that's what we do here. So we get 24 times 10 to the 9 cycles, and then this just becomes to find the appropriate clock rate. Clock rate is cycles per second. We know that the program takes 6 seconds. So therefore, on these examples, I go into more detail on the equations that you would need to on an exam. But the key thing that you need to set up is indicating that you have some sort of CPU time, and I solve it properly to get clock rate equals clock cycles over CPU time. You have the clock cycles already. We just derived it. CPU time is given in the problem as 6 seconds. So it just becomes 24 times 10 to the 9 over 6, which becomes 4 times 10 to the 9, which is 4 gigahertz. In this kind of thing, I will do problems on the exam like this where the division or multiplication numbers are intuitive, so adventure. For example, I hope that you know how to do 24 divided by 6. So for example, if you're getting some long number that has like 45 digits in your answer, you've done something wrong in the problem. Again, I'm making sure that you understand how to set the problem up, not can you put it into a calculator. Okay. Does anybody have any questions about this example? The next example is going to be a good description of how we use average CPI. So example 6, we have 2 implementations of the same instruction set architecture. So now we have computer A, a lot of these problems have computer A or computer B, and a clock cycle time of 250 picoseconds. So what's pico? And a CPI of 2.0 for some program. Computer B has 500 picoseconds. Fortunately, it's in picoseconds as well, so if you don't know the answer to it, they just cancel out. And a CPI of 1.2 for the same program. Which computer is faster and by how much? So what I mean when I say computer is faster? Execution time performance. I heard the magic word out there somewhere. I want to know which computer performs better, right? So I went over that example last lecture. If I was racing Usain Bolt, we want to know whose performance was better. His performance is better. That's why he gets hit with the Segway and my legs are fine. Did you guys see that video? Okay. For those of you who didn't, Usain Bolt, he won a race and some guy was following him on a Segway videotaping him and then somehow hits the rail. Now not paying attention, goes out and just launches right into his back and Usain Bolt just knocked right over him. So it's like you had one job, man. One job. Don't hurt the world's best sprinter. Okay, so we know that clock cycles is CPI, so this is cycles per instruction times instructions. And we know that CPU time is clock cycles times clock cycle time. So we have cycles times seconds per cycle, right? So we see that those will cancel out. Instructions will cancel out really quickly. So what we can do is we can actually figure out the execution time by deriving the number of instructions. We have a CPI, we have instructions, and we have cycle time. Now here's how this equation is broken down. Execution time equal to CPI times instructions. So this becomes cycles, and then this becomes clock cycle time. So this becomes cycles over instructions times instructions times seconds per cycle. So for each one, we already know the seconds per cycle is 250. We know that it's 2, and we know that we have the same program and the same instruction set architecture. So therefore, the number value I is irrelevant. For the denominator, you can say 500 picoseconds times 1.2 times I. We get rid of all this, and we see that that is the equation we have set up. And then you can cancel those out. So you can see what will happen here is this becomes 250 divided by picos. This becomes 1.2 times 2. These cancel out. This is 1 over 1.2, which is approximately 0.83. And here, remember, since n is less than 1, then the execution time of A is less than B. So therefore, A is faster by a factor of 1.2. So does that make sense? Basically what we did here is we know how fast the clock cycle time is. The clock cycle time is how, basically, since we're in digital systems, we have a 0 to 1, right? We have these clock pulses. And so the distance from here to here in terms of time, that is your clock cycle time. So anything from one positive edge to the other positive edge, or one negative edge to the other negative edge, that is your clock cycle time. And then how many of these you get in a second, that's your clock rate. So here we know the clock cycle time. We know that the cycles per instruction for some program, we've gone through this average CPI and come up with some sort of rubric 2.0. We have another one for 1.2 at 500 picoseconds, which runs faster. So even though it takes fewer cycles per instruction on this machine, because its clock cycle time is more, therefore A is going to run faster. So that's where and this is the reason why this is a good example, is it shows the implementation of how CPI versus clock rate. Sometimes you're going to get instances where even though your clock rate is going extremely fast, improving this with a better CPI may give you a better computer. So we had this magic number 2.0 and 1.2. Example 1.7 is example of how we came up with these numbers. So we have 3 instruction classes. The CPI for instruction A is 1. The CPI for instruction B is 2. The CPI for instruction C is 3. So for each of these 3 instruction classes and the number of instruction counts for each instruction class. So we have 2 computers. And we know that so each computer, now we have different instruction set architectures, right? So this is where understanding the underlying architecture becomes important. So I have some sort of CPI for each program. I've designed it this way. However, in order to execute this instruction on computer 1, I need 2 instructions, right? For computer 2, I need 4. For computer B, they're both the same at 1. And for instruction set C, for computer 1, it requires 2 instructions, and for computer B, it requires 1 instruction. So now we use our average CPI. And equation to do this. So this just becomes CPI times instructions, that's the sum, divided by the summation of the instruction count. So here, CPI of computer 1, we find it this way. We have, well, the equation is here, but I'm going to show you how we derive this. So the summation of CPI of I times instruction over summation of the instructions is equal to 1 times 2 plus 2 times 1 plus 3 times 2. And that's equal to 2 plus 2, which is 4, plus 6, which is 10. Now that's in the numerator. The denominator is the summation of instructions, which becomes 2 plus 1 plus 2, which is 5. So that average CPI is 2, so we have gotten the right answer. So doing that, let me cover up how B is done. How do we do the second computer?
4 times 1 plus 2 times 1.
4 times?
Plus 3 times 1.
Plus 3 times 1. So it's 4 plus 1, or 4 times 1 is 4, plus 1 times 2, so that's now 6, plus 3 times 1, which is 9. And now what do we do?
Divided by 4 plus 1 plus 1.
Divided by 4 plus 1 plus 1, so that's 9 over 6, which is 1.5. Good job, you guys got the right answer. So, determine which of the two computers is faster. Which one is faster? Why? I've heard both. Bingo. Fewer cycles per instruction, right? So I have two computers, we've compared them, I've figured out the average CPI. Since it requires fewer cycles per instruction to execute the program, computer 2 is faster. Does anybody have any questions on this before I move on to the next example? So basically what we do is we would get this 2 and 1.5, and then once you've calculated your average CPI, you could go up to an example 6. You can plug those numbers in, and then now you have your clock cycle times, you have your clock cycle times, you have your the average CPI, you know that the instruction count is the same, and you can compare the computers again. So now we can get even better comparisons. All right, so now we're going to talk about this concept of Amdahl's law. So up until this point, we have talked about a computer in terms of just this generic. We have a set of instructions. We go through with performance, and we try to figure out what the best value is. I kind of alluded that in MIPS, there are 5 stages of the data path. Does anybody remember what they are? That's just the first one. Very good. We fetch the instruction. Now what do we do? Decode. Execute.
And then some other things related to it.
Somebody over here? Well, okay, so I've executed the instruction. So first thing, I've decoded it. I've now executed. So now I have a bunch of stuff that I have out of the ALU. So what's my next step? Store. So these are the last 2 stages. I either store to data memory or write back to the local copies of the. Very good, very good. Usually it's a lot of me stammering up here and no one knows what I'm talking about. So I'm very happy that we have a number of people who already know. So the reason why this is important is because of this concept of Amdahl's law, that if I speed up, let's say I've somehow magically improved the execution time of the ALU by a factor of 2. Does that improve the entire computer by a factor of 2? See a number of people shaking no. That's correct. Why not?
Because you have to take into account the other parts.
Exactly right. And that is what Amdahl's law is. So we have this concept of speed up, which is the factor by which execution time is decreased. It is found by execution time old over execution time new. You can write on the TGO ET old over ET new. So basically, if I had a computer that was running in 10 nanoseconds and it ran in 8, the factor is going to be 5 over 4, which becomes 1.25. So now, the Amdahl's law is both the equation and the speed up. So Amdahl, this TGO 1.34 is define Amdahl's law using an equation and then describe its importance. I can say verbatim, what does that mean? Write a bunch of stars, right? I'll expect you to know that in the future. So define it using an equation. So here's your equation. So I have, let's say I have a instruction fetch takes 5 nanoseconds, instruction decode takes 5 nanoseconds, execution takes 15 nanoseconds, memory takes 20 nanoseconds, and write back takes 5 nanoseconds. So now I have 5 different stages of the data path. And let's say I have improved my data memory by a factor of 1.25, right? Factor. So this means my data memory is here. So notice this becomes 20 times 4 or 5 since we're dividing, and this equals now 16. Very good. So what this means is your execution time is now going to be equal to 20 over your factor of speed up, 5 over 4, which we've calculated is going to come down to 16. So that's your affected. Now your unaffected is going to be plus 5 plus 5 plus 15 plus 5, right? So that becomes 30 plus 16 equals to 46. So we've now calculated our new execution time. The old execution time was 50. So our speed up that we gained was actually 50 over 46, not 1.25. And so the relevance of Amdahl's law is it helps in finding the maximum expected improvement to the overall system performance when only a part of the system is improved. So there's a couple other examples in this section, but I want to go back to the job application that I showed you from National Instruments. So interested in learning about digital and computer technologies, synchronous elements, including flip-flops. You're going to computer architectures and interfaces, basic processor memory and processor interfaces. You need to be able to understand performance in order to understand these elements. So that's where understanding the performance of a computer architecture and how any improvement to your design is going to affect the overall performance. So let's say I have a computer where I have an I/O interface where I have a sample that occurs. These are going to be the last two examples, but these are Amdahl's examples. So let's say I sample every 20 nanoseconds, right? I am sampling the value. And I had an architecture that put the value there every 20 nanoseconds, right? Now, and held it, and then 3 nanoseconds later, so it holds it, 3 nanoseconds later, it gets rid of the value that I wanted, right? So there's a potential that after 4 nanoseconds, the value has changed for some reason. Now, if I improve the performance of the architecture by 4 nanoseconds, that means I'm shifting this all over by 4 nanoseconds. And if I don't account for this at the I/O level, the result is going to be that you can't guarantee proper execution of the computer. So being able to tie this to I/O, being able to tie this to interfaces, being able to tie this to underlying computer architecture is actually very important. So we're going to go into a couple of examples on Amdahl's law here in a second. So these are a couple of the Patterson-Hennessy textbook examples. So or problems. So 1.8, 1.9, 1.10. We'll do those. All right. So 1.8, given a program's execution time of 100 nanoseconds, the floating point addition, which takes up to 20 nanoseconds of the program's execution time, is sped up by a factor of 5. What is the new execution time of the project? Now that you know Amdahl's law, you're able to solve this. So it was 100 nanoseconds. Floating points take 20 nanoseconds. So what's my unaffected? 80, right? So that's just 100 minus 20. So automatically, no matter what, due to Amdahl's law, you cannot improve 80 nanoseconds. So we've improved by a factor of 5. If I say factor of 5, what's the term I'm looking for? Speed up, right? We just had the definition. Speed up. If I say factor, speed up, right? So now we have our equation. We have our effective time, which is 20 nanoseconds, divided by our factor of 5. So it goes down from 20 to 4, plus 80. So now it's going to be 84. And as you can see right here, that is precisely what we've done. So the speed up, we want, if the problem then said, what is the speed up of the overall program, you would just say 100 over 84. Okay. So the next problem is a little more like what you'd actually see in an industry problem. So we have our table showing instruction type breakdown. We have a program here that has 100 compute instructions, 400 load instructions, 100 store instructions, 50 branch, and therefore our total number of instructions is 1,550. So assuming that the computes take 1 cycle, so you can go 1, load and stores take 2, branches take 3. Find the execution time for each program on a 3 gigahertz processor. So again, without looking at what I've done here, let's solve this problem. Right, so you have everything you need. So I am looking for execution time. So what would your proposed approach be?
Each number about their CPI.
Mm-hmm. So bear in mind we have to find seconds. No, that's right, seconds. So that's going to equal. So what I have instructions and CPI, right? So cycle and instruction. So now I have CPI, right? Let me right? And now, how many instructions do I have? So I have instruction, and then seconds per cycle. So now I've got to find the average CPI, multiply it by the total number of instructions, and then do my seconds per instruction, which is the same thing as divided by clock rate. So divided by clock rate, that's the same thing as CPI times I times cycle time. Since we have 3 gigahertz, clock rate flows better. So here, the next step is to multiply them out. This becomes 1,000 times 1, 400, plus 400 times 2, plus 100 times 2, plus 50 times 3, divided by 3 times 10 to the negative 9, 3 times 10 to the 9. This is a sufficient answer on an exam. So now, does anybody have any questions about how I came to this equation? And for the record, I have no problem stopping and explaining it over again, if anybody actually asks.
And so the instructions times the CPI, that's in parentheses all over the clock.
Correct.
Okay. Okay.
Yeah. So for part B, assuming that computes take 1 cycle, loads and stores take 2 cycles, and branches take 3 cycles. So again, we have 1,000. Sorry, we have 1,400, 150. What is the speed up of a program if the number of compute instructions can be reduced by 1/2? So number of compute instructions was 1,000. So now we just do the same equation as before, except since we know Amdahl's law, we can just say 1,000 divided by 2, plug into the exact same equation, and we get the second value. And then this is the decimal value. So what you could do in part is you could go 1 times 500 plus 2 times 400 plus 2 times 100 plus 3 times 50. The gigahertz are going to cancel out. So now you can do 1 times, let me put this in the numerator. 1 times 1,000 plus, we're going to call this y, where y is equal to 2 times 400 plus 2 times 100 plus 3 times 50. So this becomes 100 plus y over 1 times 500 plus y. And that is your speed up. That will be 1.3. So using Amdahl's law, we were able to find that by just changing, we have figured out, we have a new fancy schmancy compiler, or we have a new architecture where we're actually able to accomplish the same compute instruction or operation using only half of the instructions. Therefore, we can improve the performance by a certain amount. Okay. Any questions on that before I move on to 1.10? Okay. So last, we have a set of instructions. We're given this table here. And so we have the number of instructions, it's CPI. We have the integer instructions, CPI. Load store instructions, and its CPI. Branch instructions, and its CPI. So part A. So this is a good application of Amdahl's law. I am an engineer. I am your boss. I am the boss from Dilbert, right? Like I'm the bowling guy. And I said, I need this computer work. And it has to improve by, how much can you improve the CPI if you want the program to run twice as fast, but you can only improve floating point instructions for some weird reason because it costs less. Or they cost more, and I really want the computer to be cheaper. These floating point instructions are super expensive, so get rid of them as much as you can, right? So now you have crazy boss. Now you have to see, can I actually do this? So you can use your handy-dandy Amdahl's law. You can use your equations, and you can multiply it out. So we know that our total cycles are equal to 560 times 1 plus 200. Total cycles times 2,000 times 1 plus 1,280 times 4 plus 256 times 2. And we get 8,192 times 10 to the 6 cycles. The total number of cycles is 560, right? So how much would I need to improve the computer in order to make it run twice as fast? How many cycles do I need to get rid of in order to make it run twice as fast?
4,096.
4,096, right? And how many cycles do I have available to be a floating point?
560.
So what does that mean? Not possible. Correct. Since floating point instructions do not consist of half of the instruction cycles, 560 of 892, then it is not possible. So you go back to Dilbert Boss and say, that's only 560 out of 892. And they go, well, how can you make it more? And you go, no, you can't. That's breaking the laws of physics and science and intelligence, right? So this is how you can use this to justify design methodology to a employer, to a customer. We did it this way. We can't get it down this much because of Amdahl's law. Yes?
Now, is there, now can you figure out your speed up? Can you use Amdahl's law for more than just part of the system? Can you use it for the entire system?
Well, the whole goal is to get from a part of the system to show the overall system speed up. So the point of this problem is, can I reduce part of the system to get an overall speed up of 2?
And so I'm thinking, can you reduce all of the parts of the system?
But you have to design each part of the system individually.
Okay.
So, for example, this is a good question. This is trying to make an intuitive understanding of what Amdahl's law is. So let's go back to our 5 steps of the data path. Instruction fetch goes into a memory element and fetches a 32-bit instruction. So we have memory elements. So the opcode goes to a control scene, which is a controller, which is a bunch of state machines. Some of them go to registers, which are local copies of cache. Some of them go to sign extension, and then they're all sent to an arithmetic logic unit, which has no memory elements, it just performs executions. And then you can either go to data memory or be written back to the registers. So each one of those stages consists of something very different. As you guys will learn later in the course, designing a memory element is very different from designing an executable element. So to answer your question, the reason why the answer is no is because if the design principles that will improve a sequential computer will be different than doing one that's just combinational. So you have to focus on every single portion of it and make sure timing is important, is met. We're going to be talking about these pipelining hazards in section 6, and that'll be a very important part of that to bear in mind. So the answer to your question, that's a long answer of no. That's a good question, though. Okay, so now that we understand part A, here's part B. By how much must we improve the CPI of load store instructions if we want to run the program 2 times faster? So we've done this calculation already. We already know it's 8192. And we need to, so here we have 1280 times 4, right? So we have an available 5,120 of 8192. Since it's greater than half, we can accomplish this. And so we're able to do the calculation here. Basically, this would become, let's see, 5120 minus 8192 divided by 2, right? So that's the number of instructions, and therefore we would divide that by our original number of instructions. Here I multiplied it by times 4 because that's our CPI, so now we have our improvement in CPI, which is 0.8. Does everybody understand how I came up with this equation here? 5120 is 1280 times 4. 8192 is the total number of instructions that we calculated in part A. I'm sorry, total number of cycles in part A. Divide by 2 because we want the speed up of 2 times faster. And then, so now I have my new clock cycles. Then to obtain speed up, I get my old clock cycles. So now I have cycles. And then I have my CPI. So then I'm able to figure all that out. Now, part C. By how much is the execution to the time improved if the CPI of int and floating point instructions is reduced by 40% and the CPI of load stored and branch is reduced by 30%? So this is where just writing out the equation showing me you understand becomes important. So this is a valid solution, and this is how I'm going to show you how we derive this. So the total cycles. So floating point, we have 560 times 10 to the 6 times 1, right? So we've reduced by 40%. That means we still have 60% of the instructions, right? So if it's reduced, therefore this becomes 1 minus 0.4 times 560 times 10 to the 6 times 1. Same thing, plus 1 minus 0.4 times 2,000 times 10 to the 6 times 1, right? So these are our floating point instructions and our integer instructions. So the integer and floating point instructions were reduced by 40%. So next, since we have CPI of load, store, and branches reduced by 30, what are my next values that I'm going to add are? 1 minus 0.3 times what?
1280.
Yep. 1280 times 10 to the 6 times 4, because that's our CPI, plus what? 1 minus 0.3, which is 0.7, times 256 times 10 to the 6, and you multiply that by 2, since that's its CPI. And then to find the speed up, you just divide that all by your original clock cycles, which we calculated in section A as 8192 times 10 to the 6. This is a sufficient answer. You no need to plug that into a calculator on an exam.
I guess on homework, should we get a regular number?
Get a what?
Plug it in a calculator.
If you want. I mean, the key thing is, again, I want you, since we're, one of the big debates in education is, what do you test? What's the purpose of this course? What's the name of the course? So I want you to show me that you understand the advanced digital system, right? Everything comes down to demonstrate to me that you understand what an advanced digital system is. So, would plugging that in demonstrate that level of understanding? No, right? So I want you to just whenever you're making those kind of decisions, when you're doing your homework, think about that. Because if I take out points, that means you did something to fail to demonstrate, make that demonstration. Any other questions? Okay, so that is the end of section 1. So section 2, we're going to start talking about C programming. So I sent an email out to you guys this morning. You have a few different options for compiling in C on your projects. The one that I think would be the most effective is downloading from Eclipse and being able to run that on your machine. In order to do that, you have to make a couple of edits. You have to download what's known as a GNU combined compiler, which is able to do C, C++, Fortran in one compiler. It's the standard you'll see it as GCC everywhere. That's the standard C compiler. And then being able to run Java, the Java runtime environment, the Java development kit to properly execute Eclipse. I actually, on Blackboard, I have posted this PDF in which I go over literally everything you could possibly encounter in the process of installing. I've included pretty pictures so you can see what you're doing. I've also uploaded a video to YouTube where I go step by step through it and do the installation as well. So you can actually have the PDF open and see the video so you can see what I was doing. So there shouldn't be any issues there. So you'd be able to go into something like Eclipse here, run your program, and sometimes it'll take a split second, but it's compiling all these. Oh, it's already open apparently. Cancel. Oh yeah, it is already open. I was trying to cheat. So as you can see, I have put in some C code. I'll show you how to do this. You can run it, and this is your basic hello world. what you'll find out is I'm a big stickler for commenting your code. And I believe that to be a very important skill, especially when you get out into industry. How many of you have ever written a bunch of code, Java code? I know you guys code in Java, or some of you have done C++, and you look at it a few days later and you have no idea what you were doing. Every single one of it, me, everybody, right? So and you hear, especially because of your double E's, so you're planning on taking some of the higher level classes. Speaking of Dr. Daigle, one of his very common complaints is it drives me crazy when students don't comment their code. They have no idea how to comment their code. They're never taught how to comment their code. So in this class, you'll be taught how to comment your code to industry standard. So that way you get up to control theory, take this class, and you beautifully comment your code, and he's happy. Right? And then you get out and people try to use your code later and they're happy too. So let's talk about code. So this meets these, is going to help us meet some of these course objectives. Being able to design projects in C, write a C description in a combinational logic circuit, write a C description of a sequential state machine. So we talked about Mealy and Moore machines. You're actually going to be using C to write those and produce outputs. And then using current engineering software to compile and simulate circuits, including those described in C. Your final project will be to write the entire MIPS data path in C. We'll be building it up over the course of the projects in this class. Okay, so this will provide you a better understanding of how a compiler can drive a micro engine and what code is physically accomplishing. For those of you who have taken C++, how many of you were trying to write pointers and were just like, oh, I hate pointers. I hate writing pointers. Yeah. We're going to go precisely how to write a pointer. What is physically a pointer? How you call it in your function, how you write the function, and then once you're in the function, what you actually do to allocate, deallocate, reference memory files. You're going to learn all of this. And by understanding the underlying architecture, pointers will become intuitive. So first things first, what is the C programming language? So these are two people, Ken Thompson and Dennis Ritchie. You know Thompson from your recommended textbook from KNR, Carnegie and Ritchie. Dennis Ritchie, unfortunately, has passed away. Ken Thompson is still with us and still complaining about C++. So, which I will describe a little later. So it's improvement on the B programming language, which stood for Basic Combined Programming Language. And it was a typeless language because they were trying to work on computers with low memory, less than 1 meg. If you think about it now, we all carry around phones that have hundreds of gigabytes of memory. We all have phones that have more memory than the Apollo missions. So they were doing with programming where they had less than 1 megabyte of memory. And you use those floppy disks back in the day with 1.44 megabytes of information on them. And so when we upgraded from the Program Data Processor PDP-7 to 11, so we had 1 megabyte of memory in this entire giant machine. Now, the issue is, when it came along, the typeless languages became antiquated. So it became hard to implement the B programming language on here. So we're going to learn a lot about general purpose registers in section 6 by involving types, which is your int, float, char, string. That was the innovation from B to C. And so, the PDB had no dedicated I/O instructions, only a memory bus called the unibus, and the input and output devices were mapped to memory addresses. So we're going to be learning a lot about load word and stored word operations in this course, and so that's where that comes into play. So when they invented C, they invented it in 1970 by modifying the typeless Basic Combined Programming Language, BCPL, and adding data types for variables and converting the compiler to produce machine code. So the compiler in B was simply producing assembly language, and then the compiler would take care of that. C allows you to compile it all the way down to that machine code. Remember I was talking about the difference between assembly language and machine language? by compiling down to the machine code, it can do it efficiently. As you remember, actually recall these TGOs, the difference between assembly language and machine language. The main goal of the design of MIPS is the high performance execution of compiled code. So referencing that again. And then compiler driven encoding of the micro engine. So what does this mean? By compiling down to C, by adding types and adding the ability for the compiler to go down to the machine level, we are actually able to optimize the machine language and therefore improve performance. Therefore, you're reducing the number of instructions, you're improving the compiler. Now you're reducing cycles per instruction for a program. So that's why understanding C is important, especially for electrical engineers, especially when you're doing, if you're ever coding on a Raspberry Pi, or if you're coding down at the machine level, which as double E's you'll be doing, having a thoroughly good understanding of C will improve your ability to do your work. And so, let me go past 2.1 here. 2.2, since C compiles directly to machine code, the compiler may derive code that allows significantly higher throughput. So that's 2.2. And then, as I've just said, a strong understanding of C will result in a stronger understanding of an advanced digital system. So let me scroll up past 2.1, go to 2.2 here. Now, you also need to understand what ANSI C is. So the ANSI, you're going to see this over and over again, ANSI C. ANSI C stands for the American National Standards Institute, ANSI. So C was invented in 1970, and it got standardized in 1983. So TGO 2.3 is just this. The American National Standards Institute established an unambiguous and machine-independent definition of the C language known as ANSI C. And so while you're writing this down, I'll kind of go off on what I'm saying here. So all of you have coded in Java, right? At this point, I know that C++ isn't required for this course, and some of you have coded in MATLAB, and I'm sure you all love that, right? So all of these, and the reason why understanding the architecture, the system attributes of a computer, which contribute to its logical execution and are visible to the programmer. In Java and MATLAB, they rely on the compiler as the operating system and compiler to interact to be able to go to the machine code. Oftentimes that's not optimal, and in earlier versions of MATLAB, sometimes you even had the machine code produce wrong values. So back in the 70s, 80s, and 90s, sometimes you put in sign of a value, you know you're supposed to get a certain value, you just get this weird decimal value that didn't make any sense. That was what was happening here. So that's why understanding the system attributes of the computer, which contribute to its logical execution, is important, and also understanding why it's visible to the programmer. C, by compiling down to the machine language level, makes it very visible to the programmer what's going on in the computer. So now you know precisely how it contributes to its logical execution. And so everything today, I'll go on this little spiel here, automobiles, industrial machinery, medical equipment, household appliances, cell phones, anything that requires high performance, you'll be coding in C. In 2005, there were 9 billion microprocessors. So all you guys are taking 485 microprocessor design. 8.8 billion of them were embedded with C. And most embedded systems do not support C++, so learning to develop programs using strict C becomes an essential skill. And I've included this chart here of the most used programming languages. So here's C, C++, Java, PHP, Perl. And you go down here, and where's MATLAB? You don't see it. So you can see some Objective-C here, right? So that is why I chose this programming language for this course. Students were saying, I didn't really feel like I understood how to write a program, and electrical engineers really need to know C. So that's why we're doing it. Okay, so I've included a couple of industry quotes. You'll really appreciate this one from Ken Thompson. So this one first from David Griffiths. It's an important fundamental language that requires you to understand the full stack of the technology. If you learn C, you'll understand computers in a much more profound level than if you don't. And so Ken Thompson, who wrote your textbook, and I showed you his picture earlier, he was at the Turing Awards in 2012. I got to attend this talk, and he said, when they had a lot of the old Turing Award winners, so a common question is, what do you think Turing would think of your field today, right? And so somebody asked him this question, and he said, if Alan Turing saw C, so I'll explain the issue with C++. So C++ came along in the mid to late 80s, and it was done by committee, and the problem was the guy running the committee couldn't say no. So it was just a bunch of stuff just put together. So instead of having these simple programming languages that compile down easy, C++ is kind of it's a good programming language, but it's a glob of everything. It's not very efficient. And so Ken Thompson, when discussing this, said, if Alan Turing saw C++ today on modern computers, it would be like if the inventor of the TV came back to life and saw Maury Povich. So I find some people don't know Maury Povich, so I included he's the guy, that meme who says, you are not the father. You could easily replace this with saying that it's the Kardashians. So obviously that was not a compliment. So the languages C and C++ are object-oriented. We can get off of that and go to the difference between procedural and object-oriented programming. So everything you've done up to this point is object-oriented programming. In Java, you created classes and then called the classes those are objects. In C, it's a procedural language. So you're actually going to be, since you're going down to the machine language, you're telling the machine what to do. You're telling it to do by procedure. So procedural programming, which is what you'll do in this class, uses a list of instructions to tell the computer what to do step by step. And object-oriented programming is an approach to problem solving where all computations are carried out using objects. So I'm just checking to make sure I'm doing okay on time. So C++, you're able to create objects. Java, you're able to create objects. To understand an advanced digital system, you should understand how the system attributes to the computer contribute to its logical execution, and are visible to the programmer, right? And so another thing I want to go into, and we'll be going into a lot of this and kind of using C in order to translate the inputs and outputs logically. In 386 next semester, when you take the lab, you're going to be coding in VHDL. Does anybody know what VHDL stands for, by the way? It's one of those acronyms within an acronym. So VHDL, the V stands for VHSIC, Very High Speed Instruction Computer. And HDL stands for Hardware Description Language. So you're actually going to learn how to write code to describe hardware. What I'm going to be doing in this course is I'm going to be teaching you the principles of C in a way that allows you to actually design hardware. We're going to first introduce pointers in the context of designing a full adder. And because your full adders have two outputs, right? So a function can only have one output originally. So somehow we got to get that second output from this function, this procedural function, right? Well, that's how we're going to do pointers. And then from there, we'll be able to put together a computer. So, but be able to do all this, you have to understand the difference between behavioral, structural, and physical modeling. In behavioral modeling, we'll define it here as an explicit definition of the mathematical relationship between the input and output with no implementation information. So AND gate, A and B, the sum of the full adder is A XOR B XOR C. We don't really worry about what's going on in the XOR, right? So that's where we come into structural modeling. Implicit definition of I/O relationship through a particular structure using interconnection of components. So for the first set of projects, you're going to be designing 2 input AND gates, 3 input AND gates, and then you're going to be using those gates to design a 1-bit full adder, then you're going to design a 32-bit full adder, then you're going to design an add subtractor, then you're going to use those to design multipliers, then you're going to be using them to design memory elements. So you're actually going to be designing all these memory elements based on previous functions. So we're going to be using header files, and we're going to be using class files, .c files, to be able to, I shouldn't say class, .c files to be able to actually implement this at the structural modeling level. Physical modeling deals with how the system is laid out in the physical space. We will not really be going that much into that in 385. 386, you'll be going into it a little more. If you decide you want to take digital VLSI design with me, that's basically the whole idea of the course. So that's we'll be using cadence tools to be able to actually take a MIPS architecture and actually physically make a chip. And so, again, I want to include this industry quote. Some engineers are trapped by lower-level methods of antiquated simulation techniques, and they have never made the jump to successfully simulating complex systems efficiently. By using modeling techniques of a higher level of abstraction, they can simulate their designs more effectively and achieve their objectives more easily. So here's our goal. One of our goals of this course is to be able to say, I understand what's going on at this lower level of abstraction, and then by building up, we can actually understand these higher level of abstractions. We know it's physically going on in the ALU. We know it's physically going on in the full adder. By understanding what we have AND gates, then we have our full adder, then we have our ALU, we have our memory elements using our transistors and SRAM. Being able to do this means we can actually then run code at that level. So being able to take the lower level going all the way up to the higher level will basically allow you to have a thorough understanding and make you a better engineer once you graduate. And so 2.6 is a good place to stop because I'm going to include this diagram. You'll see this diagram. This is a Gauss-Khan chart, and so we'll finish all the rest of the TGOs and example questions in Chapter 1, and then TGO 2.1 through 2.6. So let me describe what this chart means. In the whole process of designing a computer and designing an advanced digital system, you have to worry about functional, structural, and behavioral, which we'll call functional, behavioral, structural, and geometric. So what it means is we're actually doing this physical layout. It says geometric here in the TGO. I used physical modeling, right? So polygons, we actually use polygons to describe like the nanometer sizes within the transistors. So you start putting those together, and you can lay those out to design AND gates, OR gates, inverters, NOR gates. So sticks, you can actually use those to actually simplify your design, your kind of higher level of abstraction of logic. And then standard cells, this is where you're going to be, you're not really going to do the standard cells. So standard cells, you actually use these to build blocks to be able to build larger logic elements. And then a floor plan is how you would actually lay out the chip. So when you did digital systems or did circuits and you have pins on your chip, you actually want to design a floor plan to be able to optimize the amount of metal you would require in order to be able to get to the pins that you need to get to. At the structural level, transistor level, which you're not really going to study in this course, but we're going to study a lot about gate. Then from gate, we're going to go to register transfer level. At the register transfer level, you're going to be dealing with load and store into this processor, memory, and switch. So your functional, differential equations are used to describe the electrical operations. Then you start dealing with Boolean equations, AND, OR, NAND, NOR, XOR, and XNOR. Then you got your RTL language, which we're going to be learning a lot about in Section 3. And then algorithms, which we'll see doing in Section 3, Section 4, basically how do you actually implement your computer. So this chart basically describes the whole idea of how you design an advanced digital system. So does anybody have any questions before I conclude lecture? All right. I will see you on Thursday.